I'm happy to introduce our speaker today, Dr. Bhiksha Raj. Bhiksha comes to us from Mitsubishi Electric Research Lab, or MERL, in Boston, or in the Boston area. I don't know exactly which suburb, Cambridge. There you go. And he did his, before Mitsubishi, he was at Compaq for a short time. And before that, he got his PhD from Carnegie Mellon under the tutelage of Richard Stern, who many of you know, who has done some good work. And Bhiksha also did some very nice work. I got to know him even while he was doing his PhD, because he, along with another student, was the driving force behind their Sphinx recognition system. And his research interests are in acoustic robustness in speech recognition. But since then, he's also gone on and developed signal analysis techniques, which he now applies to things other than speech, like images. Today he's going to talk to us, I guess, about acoustic robustness.
I'd like to add one addendum to that.
Please do.
Cambridge does not consider itself a suburb of Boston, especially among research people. Cambridge is the home of MIT and Harvard.
Okay.
It happens to be a town on the other side of the river.
Okay, I stand corrected. In fact, I was
So, thank you, Sandeep. Let me begin by introducing myself again. I'm Bhiksha Raj. I have a PhD from CMU. I got it in 2000. From 2000 to 2001, I was in Compaq.
Oh, I didn't see your first slide. I only just kept shut.
And since then, I've been a research scientist at MERL. I've worked for several years on various topics: speech rec, speech and audio processing, machine learning, data mining. And I'd first like to give you an idea of the kind of things I've worked on. I've done a lot of work on speech recognition. Much of it has been on robust speech recognition, automatic recognition of speech recorded in noisy conditions. Some years ago, I proposed a method called the Vector-Taylor series method for noise robustness, which has become quite popular since. My thesis was on missing feature methods, and I've been on contract with Springer for several years to write a book. I can't get it done for some reason. On speech recognition systems themselves, I worked on acoustic modeling, a little bit of language modeling. I've done a lot of system development. I've been a major contributor to the Sphinx suite of recognizers and the main architect of the Sphinx for open source Java-based recognizer. There is the philosophy among the perception community that our knowledge of expectation of speech and sounds affects our ability to localize and recognize speech. So in this work, I try to model that. It turns out that a recognizer is not merely a system that converts speech to text. It in fact holds a lot of statistical information about the acoustics and language of speech. So here we use the recognizer as a substitute for a human being. In this work, in fact, one of my co-author, Mark Selzer, who was a student with me at that time, I took his best in author work last year. For the past couple of years, I've been working on articulatory modeling. Sound production is governed by the physics of the vocal tract. You can't just produce any arbitrary sequence of sounds. However, state-of-art recognizers treat recognition as a purely perceptual phenomenon. They have no consideration of the restrictions on the signal itself. There have been some recent approaches that attempt to capture these restrictions through heuristic rules and abstract statistical models, but the approach leaves something to be desired. My work, yes.
Yeah, there's something called vocal tract normalization.
Yes.
Okay.
Yeah, well, it's not completely ignored. In the signal processing end, of course, and vocal tract normalization, there are a few things involved.
Okay, which
But-
work improve dramatically. I mean, this is really a...
BTRN was the last really big step in speech recognition.
Thank you,
So
yes.
it's okay. Anyway, in my work, which I have done with Rahul Satpeshkar as well as Zathrikia, we explicitly model the physics of the vocal tract from the excitation all the way to the mouth, and try to infer vocal tract configurations through analysis by synthesis. The idea is we can thus explicitly introduce the constraints embodied by the physics of the vocal tract in the recognition process. This is work in progress. A couple of years ago, a colleague of mine, Paul Lees, came up to me with this device which he had built, which cost like $10 to build. It turns out that this is actually a complete acoustic Doppler sensor. You have a 40 kHz transmitter, 40 kHz receiver, and he wanted to know if I could use it. I could. Initially, I used it to capture the movement of facial features for voice activity detection. But since then, I've been using it to correlate facial movements with speech to improve recognition and noise. It also turns out that you can use the same kind of Doppler measurements to recognize gestures or to recognize people by their gait. In fact, we're able to get about a 90%, more than a 90% classification accuracy on people walking directly towards or away from the sandstone. So that's just to give you an idea of the kind of things I do. I have authored over 75 papers over the years, and I have about 10 or 12 patent applications and patents. But on to my talk, which is a multinomial view of speech spectra for discovery of latent spectral structures. This was done jointly with my student Madhu Shashanka, who's completing his PhD at BU, and Paris Mirakis. Let's begin by listening to a sound. This is just a sequence of notes, but now here is a more complex sound. These chords are formed of exactly the same notes that we just heard, but therefore they are more complex musical sounds. Here's something even more complex. So it turns out we are forming here, this sound is composed of basically the same notes and a few others, but it's a much more complicated musical piece. Here's another example from speech. These are just a bunch of phoneme-like sounds that I sliced out from somebody's recording. Now this lower signal here is composed entirely of what you just heard.
Where were you while we were away?
But you can actually understand what it is. It's a complete utterance. So the template sounds that we heard in the first example in each of the previous two slides composed the final complex sounds that we perceive. The notes made the music, the phoneme-like sounds created the utterances. Sound in general is composed of such building blocks or themes. Here our definition of a building block are structures that occur repeatedly when they form a signal. And our goal in this work was to learn these building blocks automatically from analysis of data. The purpose, of course, was we hope that the improved characterization could be used for better recognition, denoising, and enhancement. But we are also motivated by curiosity. It would be nice to know what the natural structures in speech and audio are. But first, we need a representation. And we have a couple of requirements. Firstly, that our building blocks should combine linearly. Just adding one building block should not distort an existing one. Secondly, the building blocks should build on top of one another. They should not cancel. After all, when you add one note, the previous note doesn't diminish. And it turns out spectral representations will give you these requirements. The power spectra of two uncorrelated signals add. So we represent signals spectrographically as a sequence of power spectral vectors estimated from overlapping segments of speech. So you might convert a signal such as this to a representation like this, where x-axis is time, y is frequency. The color of the picture at any point represents the energy in that frequency at that time. This in fact resolves to a number of vectors, each of which represents the power spectral vector for one little segment of speech. Now the power spectrogram is just a matrix of numbers. The F frequency component and the TF frame is the TF entry in the matrix. So you could assume that one could just apply standard matrix decomposition techniques like PCA or ICA to come up with additive building blocks. But PCA and ICA do not satisfy our second requirement, that the building blocks we get must combine additively, they must be constructive. The bases you will get from PCA and ICA will have both positive and negative components. For example, this is a spectrogram of a signal.
What's the goal? What is your ultimate goal?
To actually learn the kind of structures that compose.
So is it recognition? Are you trying to do recognition or what?
We're just trying at this point to derive the structures. The hope is that these structures will actually give us, enable us to develop
So
things.
it depends on what problem you're solving, whether you're doing coding or recognition. The structures, the optimal structures for this problem would be different. So unless you tell us what you're going to do,
So no.
that's true.
Okay, sure. I'm not arguing with you. I'm not arguing with you. The no comes to my goals over here. That I have a whole combination of goals that I mentioned earlier. The hope is that by going the other way, getting an appropriate set of blocks, we will be able to do a better job of all of these. That doesn't necessarily mean that the blocks I get will give us these. We have a hypothesis, we're going to try to prove it. So, this is a spectrogram of a signal that's composed of just two intermittent tones. Now if I compute two bases using PCA, here are the bases that you get. It has both positive and negative components. Now the spectrogram simply represents energy in the signal. So according to PCA, the building blocks of this figure here have negative energies at these points, which doesn't make sense. There is a technique, non-negative matrix factorization, which will give us purely additive building blocks. NMF is a linear decomposition method that will decompose a non-negative matrix to a product of two non-negative matrices. And indeed, when we apply NMF on this data, we find that the two building blocks it discovers are a tone at this frequency and one at this frequency. It even finds out exactly where the first tone came on and off and where the second came on and off. But NMF has its own restriction. First, you cannot incorporate any a priori information you might have about the structures you're looking for. And secondly, you are restricted to dealing with two-dimensional data structures like matrices, which leads us to our work. In our work, we realized that non-negative data can be viewed as histograms that have been drawn from an underlying multinomial process. So then you can hope to find the structures by simply analyzing the underlying multinomial process. And those of you who have worked on language and related machine learning methods, you'll see a great similarity between what I presented in the early part of my talk and PLSI, which is in fact used to decompose word frequency counts, which are non-negative data. We all know what a multinomial distribution is. It's where the outcome of the draw can take only one of a finite number of discrete values, like a man drawing colored balls from an urn. The probability that he will draw a ball of a particular color depends only on the fraction of balls in the urn that are of that color. Each power spectral vector in a spectrogram simply represents energy against a discrete set of frequencies, and typically looks like this panel here. So we can view this as a histogram where the height at any frequency represents the number of quanta of energy at that frequency. Then we can model this as having been generated by a multinomial process, and we can visualize the multinomial process using this ball and urn metaphor. We have an urn, it has many balls, each ball represents a frequency. So there is a picker who draws balls from this urn and eventually constructs a histogram of all the frequencies he's drawn, which is this spectrum. I can have a slightly more complex model.
Excuse me, what do you mean by a frame of the spectrogram? I'm not a specialist. You mean a time slice?
One time slice, yes, indeed.
So that's how you get the DFT?
Yes,
Okay.
exactly.
Thank you.
So now here's a more complex model. The picker now has a collection of urns, not just one. And at each draw, first he selects an urn, and then he pulls a ball from the urn. And after several draws, he computes the histogram. This is a mixture multinomial process. It's a mixture because you're mixing draws from many urns. There are two aspects here. One is the probability with which he actually selects any urn, and the second is the probability distribution of frequencies within the urn. This model simply represents the generating process for one spectrum, but I can extend it to generate the entire spectrogram like this. The picker has a fixed set of urns, and in the first analysis frame, he might select urns according to some probability distribution P0 of Z. Then he draws balls and plots the histogram, which is the spectrum of the first analysis frame. He uses a different probability distribution, P1 of Z, to draw balls and to select urns in the second analysis frame. And then, so he computes the spectrum for the second frame. In the third frame, he uses yet another probability distribution to select urns, and so on, till he computes the entire spectrogram. The number of balls he draws in any analysis frame represents the energy in that frame. So what is to be noted here is that the urns stayed the same throughout. The only thing that changed from frame to frame was the probability distribution with which he selected the urns. So the urns here are the component multinomials or bases for the source that generated the signal. And these bases are specific to the source, not to any particular frame of the signal, not even to this particular signal, but to the source. And so any signal at all for that source would be composed from the same urns. So the distribution underlying any particular analysis frame is a combination of a frame-specific mixture weights and source-specific bases. A note here, mixture multinomials are also just simply multinomials. If I covered all of these urns with a larger urn, as far as an outside viewer is concerned, he only sees a single urn, but there is a restriction. This urn is a linear combination of these urns. if I laid out the probabilities of all the frequencies in the urn into a vector, each urn becomes a point in some n-dimensional space, and the outermost of these urns will form a complex hull or a simplex. And because this is the linear combination of those urns, it must lie within the simplex. And in fact, when a speaker, when our pickup generates the spectrum for many, many, many frames, each frame is now a point within the simplex, and all he's doing is traversing a trajectory for the simplex. Yes?
Right, so the question I was going to ask is, do you have any model of how the trajectory being smooth or slow?
At this point, no.
Okay, so this is a lot like LDA then?
It is essentially a lot like
I mean, it is LDA. Yeah, with some of the priors.
we haven't got. Yes.
It's like what?
I
Can you please repeat?
Yeah, there's something called
Dirichlet
latent
allocation.
Dirichlet allocation,
Oh, I see.
which is a particular kind of generative model.
If I actually use Dirichlet priors on the points, it would be an LDA process, which is not what we're doing, because we didn't get decent results for this particular problem. Anyway, so now, what about the urns themselves? Each of the urns is simply a normalized histogram of frequencies. It's in fact a spectrum. In fact, these component multinomials represent latent spectral structures or bases for the source. And the spectrum for every analysis frame is simply a linear combination of these spectra, of these bases. And so, if we were to somehow learn all of these urns for a source, what we would really be doing is to discover all these latent spectral structures for the source. And as it turns out, the model can be learned from spectrograms with a small amount of audio, typically representing as little as 5 seconds of data, using the EM algorithm. Most of you are probably even familiar with these update rules for the EM algorithm. It's just a simple iteration of these 3 equations. It's only here for reference, but let me go on. So here are a couple of examples of the kind of structures I might discover. The top example is this sound. It's just a sequence of 5 vowels. I modeled this spectrogram as having been generated by a mixture of 6 multinomials. So these are the 6 multinomials I found. But they are better understood from this picture. Each spectrogram in this figure represents the contribution of one of these bases to the overall spectrogram. So every column here would be the contribution of this basis to the corresponding column here. And in fact, we can invert these spectrograms into a time domain signal by stealing a phase from here and computing a short-time Fourier transform. So here's what the first basis sounds like. It's just the sound O. And it in fact becomes active mainly where the speaker actually says O. There's the second basis. It's just the sound A, and it becomes active where she actually says A. The third one, the sound A. The fourth one just captured the background noise. The fifth. I could go on, but what is interesting here is that the bases we learned actually capture the underlying vowels. Here is another example. These are the first 5 notes from Bach's fugue in G minor. There are 5 notes here, but there are only 4 unique notes. I have modeled this using a mixture of 4 multinomials. Here are the 4 multinomials I found. We just found the 4 notes. And these are the probability of each of these multinomials as a function of time. And you find that the first one peaks exactly where the corresponding, the figure that this one, which represented this sound, peaks exactly where the note occurred. The second peak at the 2 locations where it occurred, and so on.
What is the complexity of the algorithm in terms of number of bases? I have the feeling it's exponential.
No, it's totally linear. There is there. It's extremely simple, complexity-wise. So what we find are we are able to discover in these examples the exact spectral structures that we know compose the sound. But this was a little bit of a cheat. I found those structures because I used this magic number 4 here and the magic number 6 here. If I had used anything else, there's no guarantee that you could have associated some semantic meaning to what you got. So how exactly do you know that we found anything meaningful? clearly there's no objective metric that we can use. But we can evaluate them through applications that exercise some of the characteristics that we expect to see in these bases. For example, if all of our structures are typical and capture a lot of, all of our bases are typical and capture a lot of structure, and if we knew all of the bases, then if we saw only a small portion of any of these bases, we should still be able to identify it, which means that you would also know what the rest of the components you did observe are. Yes?
Just to ask something on what you just said,
Yeah.
in the previous example, when you play the tones, it looked like one of the tones was composed of actually had two frequencies in it a little bit. I mean, yeah,
You have this twice. So I'm just constructing the spectrogram. This node occurs here and here, so it plays twice.
I see, okay.
So it's done exactly what you want.
Yes. Okay.
I have another question. I mean, you're basically decomposing into basis functions, but
Yes.
but bases are not, in general, are not unique.
Yes.
So I'm a little confused. I mean, in these examples, you've basically broken down into what I would call the natural bases.
Correct.
But a lot of that may have to do with the fact that the signal itself, you play one note, play another note, and so
We
on.
shall see some more examples. And again, as I said, there's no objective metric. We can't even expect that we will always get something that has semantic meaning. So we have to evaluate it through other mechanisms, which is what we shall see.
I think with different initializations, you get different bases, right? And
Some minor difference. We'll get to that. So, now how can I actually evaluate what these bases are? I'm going to try to apply them to a problem that exercises some aspect that we expect to see in the bases. Like if I know all the bases and they all have unique structure, if I just saw a small portion of it, I should know which basis it exactly was, which means I know what the rest of the structure was. I should be able to perform bandwidth expansion. I should be able to predict unseen frequencies. Secondly, if all of the bases, if the bases of a sound capture all of the typical structures in that sound, then we should be able to extract the signal components for that sound from clutter. So we should be able to perform denoising and signal separation. So here's an example of bandwidth expansion, the telephone bandwidth signal. It only has frequencies in the 300 to 3500 Hertz range. Based only on these, can you predict what the rest of the frequencies were? From a ball and arm perspective, we have the picker who has his urns, who's drawn the histogram, the spectrum for the first frame, the second frame, and so on, and constructed the entire spectrogram. Except that we are not able to see all of his draws. We are only able to see the number of times he drew these frequencies. And based on these, we must guess how many times he's drawn these other frequencies. Here is a simplified version of the problem to convey the idea. Let's say he had only one urn with only red and blue balls in it, and you were informed that he has drawn the balls some unknown number of times, but m of these are red. How many were blue? Now here is a very simple solution, not necessarily the best solution. You can estimate the total number of draws as the ratio of the number of red balls to the probability of drawing red. And from that, you can estimate the number of blue balls. Now, if you have a multinomial rather than a binomial, it gets more complex. So the overall procedure for bandwidth expansion would be this. We learn the urns for the signal from some broadband training data. Then for each frame of the reduced bandwidth test utterance, you find the mixture rates for each of the urns. And you only use the frequencies you observe. The assumption being that if the structures are distinctive enough, these should still give you an idea of how much each of the bases, each of the components occur in the signal. Then you have a complete mixture multinomial for each frame from which you can estimate the unseen frequencies. So here's an example. This upper one.
But given Bank of America's recent track record, double quote, you don't necessarily
It's a
want
full
stability.
broadband signal,
Says,
having frequencies from 0 to 8 kilohertz.
Longtime executive vice president.
I passed this through a 10th order Butterworth filter that removed everything below 300 and above 2500 hertz. So this is what it becomes.
But given Bank of America's
You can
recent
hear
track
that this
record,
band-limited signal is
you
muted.
don't necessarily want stability.
Now, I learned the urns from a collection of training data, which did not include this
Executive
urns,
vice president, period.
and estimated the upper frequencies. And you can see even visually that we've actually done a reasonable job predicting exactly what the upper frequencies might be like.
The training set has a full bandwidth.
Yes.
Yes, obviously.
Because the urns have to cover everything. And here's what the reconstructed signal sounds like.
But given Bank of America's
It
recent
sounds
track record,
very close to the original
you don't
broadband signal that we
necessarily
began
want
with.
stability, comma, double quote, says Alan's handbook.
So-
There's significantly less noise in the reconstructed frequencies than in the real ones.
Well,
But if you've done some denoising on the side,
yeah, I'm not, I guess, that's primarily because it's an estimate, so you're not going to be able to estimate the fine structure, which actually sounds like noise.
The training data contained the same speaker?
No, the training data was for the speaker, so we're only showing it. But if you want speaker independent, you can't. You haven't yet managed to get it to be speaker independent, but you can do it over a set of speakers.
Yeah, but in principle you should. I mean, you put a constraint on the physical where the formats occur, you know, so you'd be able to iteratively go and do that. So in
Yes.
principle, it's not undoable.
In principle, it's not. There are some minor issues which I mentioned in the last slide. Okay, so the problem of signal separation from monaural recordings. Here you have multiple sources producing sound simultaneously. You recorded them over a single microphone, and you would like to selectively enhance one or more of them.
Before you go, let's go back to the previous one just a little bit. So instead of looking at it as, finding the basis from the broadband signal and trying to guess what's going on using the narrowband, you could take a completely different approach. Suppose I built up a speech synthesis system from all of the data that you're going to train on. And then I simply did some kind of synthesis for whatever pitch contours I can extract, because that I can do on the, maybe not the F0, but you can get most of the contour information from the narrowband, and then just resynthesize it.
And we shall mention that in a few slides down. Okay. So now, the problem of signal separation. Now, the assumption was that every source has got a distinct set of spectral structures for that source. In other words, every source has a unique set of urns. We'll also assume that the urns have actually been learned beforehand from some training data. For the mixed signal, in the mixed signal, a second level process simply combines the signals for the two sources. So the statistical model could be represented by the second column. In each draw, he randomly selects one of these two pickers who selects an urn and draws a ball. And then you compose your histogram of these draws. The total number of draws of any frequency in the spectrum therefore includes contributions from both sources. And what we really want to do is, given the histogram of draws from both sources, we want to estimate how many of the draws came from source 1 and how many came from source 2. Now, the probability distribution for the mixed signal is a linear combination of the probability distribution for both sources. This term here represents the contribution of this source, this the contribution of this source, and the distributions of the individual sources in turn are mixture multinomials according to our model. So this is the probability distribution for the complete mixed signal. We also assume that we know the spectral structures, the urns for each of the source. So what that means is these remaining parameters must be learned from the mixed signal. And it turns out you can do that once again using EM, just an iteration of 3 very simple equations, which I put up here for reference. But once you do that, you actually have all the terms in this equation. So now you can block out the sources that you're not interested in and selectively estimate the number of draws for the desired source using a very simple formula. Interestingly, even if you knew the urns from only one source, you can still do the same thing. Then, in this case, you would estimate the urns for the second source along with the rest of these parameters in the process of learning. The rest of the separation procedure stays the same. So here is an example. Here are a couple of examples. This first one is a piece from Raise My Land by David Gilmour. It's just got some lead guitar, some background music, and our intention here is to separate the lead guitar from the background music. We've learned the basis for the background music from 3 seconds of music on these segments. Here is the separated lead guitar. And separated background music. And the second example will be, we have Nora Jones singing Sunrise.
Sunrise, sunrise,
We want to separate the vocals from the background music, except we have a problem. The signal was clipped, and clipping introduces non-linearity. Yet, here are the results we get. The separated music. Yes?
I don't get the insight why clipping there affects your.
Okay, that's
your
simply because
processing.
we are assuming that the building blocks combine linearly, very big in the very beginning.
I see already. Okay.
Right. Of course, Mitsubishi had to apply to a product. So here are some examples of denoising. We did this for Mitsubishi cell phones.
So in the EM, couldn't you take the when something hits max? Couldn't you take that as reflecting uncertainty about the actual value?
Yes, we could.
To compensate for the clipping.
Yes, we could, but we haven't done that yet.
Right, but am I right to think that it would be relatively straightforward? I'm not positive.
I'm not positive. I think you're right, but I can't say for certain. I mean, it makes sense that it is such an speculative. So these examples over here are just various of my colleagues speaking into a cell phone with various noises in the background. This is someone speaking when a phone is ringing in the background.
Okay, so let's see how this goes.
You can hear both. Now this here is what you would get if you use the standard denoising that is part of the 3T standard right now. You can't do anything about a ringing phone in the background.
So let's see how this goes.
And here's what we get.
Okay, so let's see how this goes.
The phone is completely gone. Here is another example. This is Paris speaking while an Aibo robot is tromping around in the background.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
So
1, 2, 3, 4, 5, 6, 7, 8,
you're training
9,
data just
10.
for the speaker, or just
no,
for that speaker? Or
everything is done off this. So they're just using the first couple of seconds to train the basis for the noise, and then do everything else on the fly.
That's why your phone ringing tone was there before any speed started.
Yes. But the point is, for the standard Wiener filter, the same structure is still there. So the comparison is totally apples to apples.
So how many components do you use, and how do you decide which ones to recommend?
Okay, we compute, depends on the amount of training data, between 25 and 40 components, and we use all of them. So we don't combine the components for the competing sources, only the sources that we are interested in.
But how do you know which one?
Okay, that's because we have learned. So, for example, in the denoising case, I learned about 25 components from those 3 seconds for the background music. And then I learned 30 components for the other source. So I know exactly which components correspond to which source.
So this is where I'm not following. I thought that sounds like you have some kind of label data. For that, where the sources are already separated. I'm not sure you were getting.
There is an assumption over here that the sources are not separated. I have data for just one source, not necessarily for the second source. So when you start playing a song, the first 3 seconds you can normally assume represent just the background music.
I see. Okay, so the phone comes in later.
Yeah, in this case,
You need
the phone
one
comes first.
The phone came
This
first.
is the phone came in first. Okay.
Yeah, but you had 1 second of phone rings, and that was sufficient to learn everything you wanted to.
Right. So you didn't play us the answer that this actually gave us, which was to think that the phone was the signal and the speaking was in there.
No, I mean you can look at it either way, right?
Yeah, sure. Right.
So it's totally symmetric.
I mean, it would be easy to do a classifier that told which things were speech and which things were noise on that.
Not necessarily always. Sometimes it gets very complicated.
So put it another way, if you knew some region where you knew only one source was active, that's enough.
That's sufficient.
And then the rest of it, they can both be mixed.
Absolutely.
Pick out the model for the first source from that known region, and then the
rest
other
is-
one gets learned.
I mean, it's very interesting, and it would be interesting to see how this compares with other algorithms that actually assume no prior knowledge on the signal's success.
For denoising, so okay, for signal separation versus denoising, this is the denoising. This is what you get with what is part of the 3G standard, which was proposed by Mitsubishi, so I have the code. Same signal, nothing happened. It's still
Okay,
there.
so let's see how this goes.
So, in that sense,
Well, I don't know the standard. I mean, I know that there is a lot of work on separation of sources.
yes.
You know, using
So
all
I will
kinds of-
mention that in the slide. Okay. So now, in this slide, now, as I mentioned, in order to be able to do the separation or the enhancement, I expect that the spectral structures we have learned are typical for the source. But now, when you have speech from two speakers, the speech from different speakers have structures which are very similar. So the structures may not be unique, and you really cannot expect, according to our original hypothesis, to do a tremendous job of separating speech and speech. So here is an example of speech and speech.
The Treasury commissions can also reduce the investment value of life insurance policies that include savings component, such as...
Now, both of them are speaking. One is male, one is female. I've obviously chosen the male and female to make them as different as possible. I learned 40 component multinomials for each of the speakers from 5 seconds of separate recordings. And here is the separated signal for the female that I got. Here again is the mixed first.
The Treasury commissions can also reduce...
And then here is the separated one for the female.
Higher commissions can also reduce the
We
investment
actually
value
end
of
up
life
getting about a
insurance
5 dB
policies
improvement
that
in
include
speaker
savings
interference ratio.
component, such as universal life policy.
And
The Treasury market got off to a weak start on that.
so we end up getting about a 5 dB improvement in speaker interference ratio. And there are lots of methods out there that can do much better than that, except that the total amount of training data we've used, that is 5 seconds, is really small compared to the method, to the supervised methods. And the computation we use is maybe 2 orders of magnitude, anything lesser than anything you do using unsupervised method. But we're not happy with this result. Anyway, the idea was you're supposed to be able to learn structures. Now, the math technique itself is not specific.
Let me ask you another question. Let's go back to the previous slide.
Yes.
So you have 5 seconds of data from the male and the female speaker. You estimate your bases from those. And then with this new signal, you're simply treating it as a separation problem.
Yes.
What if you try to re-estimate your bases as well from that signal? Would that really go into some la-la land and create some strange bases?
You get a slight improvement, but not a whole lot.
Oh, it does improve. I would think it would get worse.
No, it doesn't, because you have to start off from a good point, but it's totally unsupervised. As a side note, now we actually use this for recognition. So we can actually learn the bases separately for each of the speakers, and then compute mixture weights for every frame for the bases for each speaker. And you'll remember that Martin Cook had a speaker separation challenge in September. The best system by far was a system from IBM. Now we used our mixture weights as, it turns out although separation is not great, we beat everybody when it comes to recognition. We use the mixture weights as state output probabilities and just ran a bit of decoding on top of it. And we were within about 5% of the IBM system on every condition. We did submit the results, Mitsubishi just wasn't interested, but had we actually submitted it, we would have been the second best system by a pretty big margin. With the caveat that the computation we used, this is linear in the number of speakers. So we would have been about 10 to 50 times faster than anything anybody submitted. So, it's not just separation. There are many things you can do. Now, I use the same thing to learn 49 component structures from a collection of faces, over 2,500 faces from the CIDL database. Here are the bases you discover, which are cards of faces, which is similar to what you get using non-negative matrix factorization. I ran the same thing on a collection of the text processing people here might be familiar with the NIPS corpus, which is just word count vectors from all papers under 2003. Now, the papers in NIPS typically fall into 3 categories, which are, I think, neuroscience, algorithms, and theory. So if I learn a mixture of 3 bases for this data, I would expect to find the papers to segregate into these 3 categories. It turns out that that's not really what happens. Here, the red, green, and blue dots are examples of papers from the 3 categories, and they don't really seem to segregate out. And as it turns out, this is exactly the result you get using PLSI, and it's not very useful. So as you see from this last example, although we get some structures, they're not always that good. So here comes the question, are these representations sufficient? Now we know that the urns represent latent structures in the signal, spectral structures in the signal, and any sufficiently complex sound source will have many latent structures, which means to actually sufficiently represent it, you want to learn lots of urns. But then here you run into an arithmetic restriction. You cannot reliably learn more urns than you have frequencies. You run into indeterminacy, and you can end up with trivial solutions. best explained with pictorially. So for illustration, here I have assumed that there are only 3 frequencies. This gray triangle is the unit simplex, 3-dimensional unit simplex. The corners are 0, 0, 1, 0, 1, 0, and 1, 0, 0. Any probability vector, thereby in our model, any spectral vector must lie within the simplex. The blue dots here represent an example distribution of data that you might have. Now, when you learn a mixture multinomial to represent the data, what you are doing is to learn the corners of a simplex that encloses this data as compactly as it can. And if you've got a compact enclosure, then the corners of your simplex might be thought of as being representative of the distribution of the data. And any data points that fall outside the simplex, like this one here, are being modeled with error. And we also try to minimize this error. Now, if the number of corners is the same as or higher than the dimensionality of the space, here is a trivial solution. I can simply put these corners out here, and I am guaranteed that I'm going to enclose every probability vector perfectly with no error. But this solution is meaningless. I mean, these corners don't tell me anything about my data itself. And I would like to avoid this trivial solution, and here's how I do it. I allow this source to have an arbitrary number of components. But I require that any particular data vector be composed of only a small number of these components. So, for example, the speaker might have any number of urns, but he can use only this subset for the first frame, this subset for the spectrum of the second frame, this for the subset of the spectrum of the third frame, and so on. What this implies is that
you're throwing information now.
Pardon me?
Until now you haven't been throwing any information, but now you're beginning to throw.
The only information I'm saying is that it's got to be sparse. I'm not saying which particular urns must be chosen. So now what this really means, implies, is that we are saying the source can have a large number of spectral structures, but within any particular segment of speech, only a small number of these structures are present. In terms of simplexes, we want to find the corners of the simplex such that any spectral vector is close to a small number of corners. Now, since only a small number of urns are allowed to be active for any frame, it means that the probability that the speaker will select any of the rest of the urns, which is a very large number of urns, is going to be very small. Alternatively stated, we can say that the entropy of the mixture weights for these urns is very small. Now, so this requirement can be very simply enforced. We reformulate our problem. We want to estimate these urns such that the entropy of the mixture weights for every frame is minimized. And we can do this by imposing an entropic a priori probability distribution of the mixture weights, which basically penalizes mixture weights with high entropy by enforcing a low probability on them. And just a little bit of background, what I have just presented is what is called a sparse overcomplete representation. It's overcomplete because you have many more bases than you have frequencies. It's sparse because you're only allowed to use a small subset of these for any given data vector. Sparse overcomplete representations have been around for a while. In 92, Holzhausen and Fields had a very nice Nature paper titled Sparse Scoring of Natural Images Produces Localized Oriented Band-Pass Receptor Fields. Their thesis here was that images can be described in terms of a small number of descriptors from a large set, which is very analogous to what we're doing. And they define sparseness in terms of a low entropy code. Since then, there has been a lot of work on sparse PCA in both the statistics and the signal processing community. The idea there is to find eigenvectors with few non-zero elements. Recently, there's been a spate of work on sparse NMF. And in all of these, sparseness is usually defined in terms of the L0 norm of the estimated bases. L0 being hard to optimize, you approximate it using L1 or some later norm, and you get linear quadratic or non-programming solutions as a result. In our approach, we are actually explicitly optimizing the entropy as originally proposed by Holzhausen and Fields, but more importantly, although I'm not actually presenting it in this talk, we have the ability now to impose any additional information that we might have about the structure of the bases within the EM framework. The update rules to learn the bases don't change very much as when in comparison to the basic model, and henceforth I'm going to call the basic model the compact model to distinguish it from the sparse model. The only thing that changes is the update rule for the mixture weight, which becomes this. The W here is Lambert's W function, and the alpha here is a sparsity factor. You can tweak it You can increase it or decrease it to make the solutions more or less sparse. Now, here is a visualization of how this affects your solution. In this example, I've generated 4 clusters of 3-dimensional probability vectors, which I've put inside the unit semplets. Now, the first 6 panels here show you the kind of decompositions you would get if we used compact learning, this basic model. Here I've represented this, the distribution of this data using these 2 multinomial components. Here it's 3. Now, remember that our solution is iterative, so depending on the initialization, you will get different solutions. So in each of these subsequent panels, you have many simplexes. Each of them represents one solution, one run of the algorithm. Now, as in the compact estimator, as I increase the number of bases, this is what happens. This is a 3, 4, 5, 7, and 10 bases. As you increase the bases, the solution quickly diverges towards the trivial solution, which is the unit simplex itself. Even when it doesn't go that far, it doesn't really capture very much about the distribution of the data. Now, in the lower panel, I've picked one of these solutions, and I have gradually increased the sparsity going left to right. And you find that once you begin increasing the sparsity, the solutions quickly converge till they nicely enclose the original data itself and capture its structure. Back to our vowels and music example to see exactly what this does for audio. This was our vowel data. The left spectrogram shows the decomposition we got when we used compact learning. If we enforce sparseness, the solution now becomes like this. You can see that now the bases are active in a much more localized manner. They are active only for almost exactly where the corresponding sounds occur. I won't be playing these sounds out, I may not have time, but anyway, you'll have to trust me on this. The bases also capture more of the structure of the vowels themselves. Why? Because over here, the bases continue to be alive even at other times. Although this one peaks, for example, over here, it still has energies in all these other frequencies, in all these other time instants. As a result, what happens is that some frequencies can leak from one basis to the other. So although this represents the vowel E, the lowermost frequency over here simply shifted into this other basis because this other basis continued to have energy over here. Here, by being forced to be very localized in time, you don't allow that to happen. This lower one is the music example, the 6 notes. Again, this is what we got using the compact learning, and this is what you get using the sparse learning. You can find that, once again, the bases are much more localized. In fact, if you hear them. Yes.
Well, in Brand's work on entropy minimization, also you had some kind of greedy algorithm for gradually becoming more sparse.
Yeah.
So what are you doing? You
so
say
you don't
gradually
all that
become more
annealing is generally not useful. It's totally useless.
So what do you do?
You just start straight up random initialization.
You randomly initialize it at each step when you become more sparse.
No, well, you just each sparsity at each degree of sparsity is a different solution. Yeah, that's right. Okay. So, but you could try to anneal it. It doesn't give you vastly different solutions. Okay. Anyway, that's it. So, okay, what happens here is that the notes actually end up sounding much more crisp, and they once again capture more of the spectral structure for the notes. Something interesting happens in this particular example. If I try to analyze the largest segment of the music, which includes chords and individual notes, if I use the compact learning scheme, the bases end up representing notes and chords. But some notes will get deleted from the chords because they're already represented by the separate bases for the notes. Whereas when I use the sparse learning scheme, chords will be complete as will the notes because you're forcing them to be localized.
Localized in time.
So they end up being localized in time because you're only allowing a small number of them to be active at any time. So the bases end up being localized in time.
Right, but the sparsity parameter is strong enough in these experiments that some of the components actually do represent C major.
Yes.
And not just not the individual notes, because then you can get away with fewer parameters.
Yes.
Zero coding that structure.
Yes.
So an interesting question is, so of course, those of us who work on things like parsing naturally think, oh, hierarchical models. And it's interesting that one of your bases, one of your components is C, E, and G together. And doesn't it happen to look like a sum of 3 of your other components?
Right. I suppose in principle it should, but but because you want to use the smallest number of bases in any frame, you're better off using the mixture of C, E, and G than C plus E plus G, so it just happens naturally.
No, I understand, but you might be able to sharpen that behavior even further.
Yes.
If you could say that it was good for one component to be close to the sum of some other component.
Absolutely, and this can be done by imposing priors on the mixture weights. Exactly.
So fun direction.
Yes. So
I mean, similar things have been done in text, where people are trying to learn phrases. For example, and you discovered that there are morphemes in words, and then you have two phrases and larger phrases together, and so there's some structure in the model. You don't learn phrases as being independent from one another.
Right.
That's phrases that are made up of other phrases.
Right. So okay. Now we know that we're able to get better. What seem to be more complete structures, but how do we evaluate them? Again, I'm going to use this. I tried them on this speaker separation problem I had earlier. Since we're running out of time, I'll ignore this panel, but here is the original signal.
Higher commissions can also reduce the investment value of life insurance policy.
It's a mixed signal. And now, earlier, using compact bases, compactly done bases, we got about a 5 dB improvement in signal to noise, speaker to interference ratio. In this example, I'm actually trained 3,000 bases. This is an overcomplete set using the sparse learning mechanism, and I had to use about 5 minutes of training data for this. And here's what I get.
Higher commissions can also reduce the investment
Now I get about a 10
value
dB
of life
improvement
insurance policies
in speaker to interference ratio as opposed to the 5 I had
such
earlier.
as universal life policies, period.
The treasury market got off to a weak
It's a
start.
much better result than I had earlier.
We're limited stock.
And here are some more results on the same thing. I ran the same thing on a mixture on several mixtures. So I categorized the results by the gender of the two speakers here. The x-axis represents the improvement in speaker to interference ratio for one speaker, the y for the other speaker. Each dot represents one mixture, so one experiment. The red results are what you get using compact learning, and the blue results are what you get using the sparse learning. And in fact, we find that on every single example, going from compact learning to sparse learning improves the speaker to interference ratio by a factor of 2 in dB. As you can see, this goes up to over here 6, this goes 10, and so on. Applying this to other data sets again, now the lack of time, this was the result we got using just the sparse compact learning. These are the bases we found. Remember, I told you that we can tweak the alpha factor to increase or decrease the degree of sparsity. If I make the mixture weights really dense, then these are the bases I find. The structures we discover are parts of faces, a little curve of a cheek, a little bit of shape, an upper lip. But then as I make the mixture weights sparse, the structures we discover are these. So each basis now represents an almost complete facial structure. And according to this model, every face in the database was composed of just these faces. And in fact, the fit is quite good. Going back to the text example, you'll recall that on the NIPS corpus, I didn't get very good separation. I didn't get very good decomposition. But then I increased the sparsity. These are 2 degrees of sparsity, 2 different levels of sparsity. This is less sparse, more sparse. The red, green, and blue dots are 3 different topics, examples of 3 different topics. Even if I increase the sparsity just a bit, the solutions begin to segregate. At high levels of sparsity, you can see that the red, blue, and green dots are just diverged to 3 corners. And every single paper in the corpus is either fallen into one corner, saying it's entirely belonging to one topic, or a combination of no more than 2 topics. So all of this is automatic. We have not annotated the data in any manner. So we're effective at learning structure, extracting structure. Once you actually make it over complete, you can extract better structures than using just the basic model. However, the structure discovered is at the level of entire records. For example, each basis spans the entire frequency axis for a complete image. How can we actually discover structures that extend beyond a record or are smaller than a record? We can do this using what we call a shift invariant version of the model. The shift invariant model, now each of our component multinomials is not just a spectrum, it's a time frequency patch of this solid. So when I drop a ball from the urn, I'm not just getting an F, I'm getting a TF pair. So according to this model, in order to compose the spectrogram, at the first analysis frame, I would draw TF pairs from all of the points and fill up the histogram in this region. Then advance one frame and draw TF pairs according to a different mixture weight and fill up the histogram here. And then advance another frame and so on. The rest of the arithmetic stays the same. The model is basically the same model we began with. You can also enforce sparsity. So here is the result we have. This is in this example, my colleague Paris and I are both speaking. He's just saying 1, 1, 1. I'm saying 2, 2, 2. And we are not synchronized. Here is the recording.
1, 1, 2, 2.
And we explained the spectrogram as a mixture of two patches. And here are the two patches we found. But this first spectrogram is the contribution of the first patch to the signal. Let's hear it.
1, 1, 1, 1.
And the second one is the contribution of the second patch.
2, 2, 2, 2.
So we find we can actually find an entire time frequency structure that represents a complete sound. And we are actually able to get a much better idea of what the structures themselves might be, which relates to your speech synthesis problem. This is exactly the same approach, except that patches are automatically learned.
How much data did you use to learn this?
Pardon me?
How much, did you have any raw data from the speakers to learn this?
No.
This is just the composition on...
Just plain decomposition. So now I can actually make the models more complex. Over here, the patches are the height of the entire spectrogram. I can make the patches smaller. So now I can begin capturing local structure, which is what I call shift invariance in 2 dimensions. I can allow the patches to scale, to rotate or twist or distort in any manner. This is what I call generalized transform independence. Also, in data, higher dimensional data like video, you might find localized structure along every dimension. It turns out the arithmetic doesn't change greatly. Now, the patches are just multidimensional. The rest of the arithmetic, including shift and transform invariance and sparsity, all of it can still be enforced. So here are some final examples. Over here, this is a group photograph, and I tried to explain this as having been formed entirely of just one patch. And here is the single building block I found for this image. It's just an average face. This is the probability with which that patch occurred at various locations. I enforce sparsity in my solution, and you find that it peaks at almost exactly the same locations where the faces occur. This is a slightly more complex image.
What did you say about supervision on the last example? Was it completely unsupervised?
Everything is unsupervised.
Yeah, so you just worked on a single photo.
We just all we said was that this image has been formed, has been composed by one patch.
But you didn't say what the patch was.
No, nothing.
Right, and you didn't say how big. You said something about how big the patch was.
Right now, we assume the size of the patch, but it's not necessary. We can actually put a proper distribution of the size of the patch.
Good.
So, and in fact, we can actually try to estimate the number of patches, but it becomes a slightly tougher problem. Now, here is another example. This is many repetitions. They're not unique. Each of them is a different rendition of the character A, or the character R, or the character L. And we try to explain this figure as using a mixture of 3 patches. Like here are the 3 patches we found. We found that the first one looks like an A, the second like an L, and the third like an R. This is the probability of occurrence of these patches at various locations. And we actually discovered exactly where the A occurred, exactly where the R occurred, L occurred, where the R occurred. Here is an example of transform invariance. Now, this is again the same thing. Many repetitions of A and L, except now I've allowed the characters to rotate and twist and so on. I've tried to explain it using 2 patches. And I find that the first one looks like an A, the second looks like an L, and I can actually find out exactly where the A occurred and where the L occurred in the image. This is a sad attempt at collapsing a video into one image, but this was actually analysis of a 4-dimensional object, a video. A video has x-axis, y-axis, time, and color, 4 dimensions. And in this video, we had 3 objects, this one, a rubber band, and then we had a ball going around in a circle. So I just collapsed all of the frames into one image to summarize, just to put it on the slide, to show you how the ball works. We tried to discover 3 objects. We found the ball, the rubber band, so the work is of course not complete. It's very much work in progress, and the shift and transform invariants in particular were not invented primarily to analyze images or video. We wanted to be able to identify localized objects and spectrograms for computational RTC and scene analysis. We're working on that. temporal extensions, other kind of priors like the LDA model, or even using mixture Dirichlet's are things that we're obviously working on. We are very interested in dealing with incomplete data. The Netflix database, for example, has 20 million records of 17,000 dimensions each. All numbers are positive, but in any given record, of the 17,000 dimensions, only 16,990 are not known. Can we still come up with a decomposition for these things? Then in speech, the difference between speakers is essentially, one of the main differences between speakers is the pitch. And we can, by analyzing speech using what is called a constant Q transform, differences in pitch simply become a shift in frequency, a vertical shift in frequency, where the structures become very similar across speakers. Once you do that, you can use our two-dimensional shifting variance model, decomposition models, to come up with to find out speaker-independent structures. We're working on that. Text processing, this is something that we've just begun looking at. You can try to use the sparse decompositions to come up with latent topics. And using the same technique we use for bandwidth expansion, you can now cope to adapt your language models using a very small amount of data. Multidimensional extensions to video are of course obvious. Also, on a more fundamental, more theoretical front, it turns out that the sparse latent-variable decomposition seems to be performing independent component analysis. We have a partial proof for this, but while proving this has been relatively simple, coming up with an algorithm that will consistently do ICA on non-negative data has been tougher. We're also working on sub-rank ICA, unsupervised supervision of component source. And finally, everything here has assumed positive-only data. But guess what? You can extend it to positive negative data. You can represent positive negative data as the difference of two histograms. And then the rest of the maths applies, including sparsity, transform, and variance, etc. We worked out most of the maths of this, but we haven't actually tested this out in much data, and this is work in progress. So in summary, I've shown you discrete latent-variable decomposition-based techniques for analyzing audio, image, and other data. I've been able to extract over complete sets of latent structures which appear to be semantically meaningful to some degree. We can detect substructures within data, as I showed you with the face examples, and there are many avenues for future work. Some references, thank you.
In the problem of the demonstration you conducted of two speakers, where I believe you were estimating or measuring the bases on the fly and then identifying the speakers, and when you played the result of each basis separately, I could hear the other speaker.
Yes, because
okay.
This is absolutely. I mean,
No, this is okay. There is an iterative scheme in some related technology where you would perhaps do some map estimation on each of the two and then pass the estimates back. In computer science, they call that belief propagation. I don't know what they. Yeah. Does that work for this sort of thing?
So, we can actually embed the whole thing into a BP framework. If you think of it, the difference between BP and the difference between BP and what we're doing is like the difference between non-negative matrix factorization and probabilistic matrix semantic indexing. In that you don't necessarily have to associate the probabilistic meaning with the components. What you get is a density. So there's similar extension exists over here also.
Very nice results. I'm going to go back to my first question, which is your work. I mean, your work is aimed. We talk about PCA and all that. Are really reconstruction or coding the signal so it can be represented in a parsimonious way. Not for the goal of actually doing recognition. I mean, you show a few examples.
I actually have results of classification.
Okay, but I mean, on large. Because every time there is this cliche, especially in the speech community, that every time you do anything with your data, you massage your data, you're going to get worse results. You know.
You're absolutely right, and we tried very, very hard to actually come up with to use just these basic representations directly for recognition, and it wasn't very greatly useful.
Yeah. No, I mean, so this would be. I mean, I was asking you if I've done it. I mean, we should think this is something instead of capture analysis, you know, at that level, you know, where you really do some decomposition and then you go and do everything else that needs to be done.
Yes,
okay.
Absolutely.
I'm just trying to understand how it fits.
Absolutely. So basically the point is if you can come up with reasonable structures then representing data in terms of these reasonable structures is likely to give you a better representation. So I deleted a slide because I thought I wouldn't have time, which had to deal with classifying characters. There's the MNIST database, which has lots of handwritten characters. And we find that if you actually learn bases in this manner, if you just use the compact code, you don't get very great classification. But as you increase the sparsity, the classification accuracy quickly improves. The error goes down to almost nothing. But it's representation based on these patterns and not using the patterns themselves.
Can you also react differently to what Andres said? Namely that I think what you said is right, that if you do some fancy signal processing up front and then present that signal to the recognizer as the signal captured by the microphone, then you're right, there isn't much you can do which will improve recognition directly. But what I thought is that in this case, for example, in the speaker separation, you're of course listening to the separated signal, but underneath there is a model of each speaker.
Yes.
And so you could feed that to the recognizer.
Yes.
So you don't have to do
Yes.
anything to the signal.
And that is in fact exactly what we did when I mentioned the speaker separation challenge. We use these as models,
Yes.
but embedded within an HMM. And we got fantastic results.
No, I know. I mean, that's why I want to clarify that this is not necessarily the old cliche way of doing things. I mean, you could.
Oh, you're saying this is okay.
Yeah, I mean, I was trying to understand how it would fit. You know, you're not reconstructing the thing to connect with.
No, it can fit in many different ways. Now, these are all left to be explored.
No, the only downside would be that if you wanted to do this in a speech recognition setting, you'd probably have to have a recognizer architecture model behind it, which says there is going to be one speaker that I'm interested in, plus there are going to be all these other things that I'm not interested in.
Not necessarily.
Right. So, I mean, all we're interested in saying is that, okay, so here is the problem, that the patterns that you learn are very speaker specific.
Right.
But if you come up with a representation where the patterns you learn are not speaker specific, which is what I mentioned using the constant Q transforms, then you can expect to use the same pattern for any speaker, in which case the variability goes away. The biggest problem we have right now is that the specificity for the speaker, because the patterns are specific. But we know how to deal with that.
Right, no more questions.
Yes. Go ahead. Yeah. I was going to ask more about the transform invariance. So the simplest way to do it, and I'm not sure if this is what you're doing, is to whenever you re-estimate, to throw in lots of transformed versions,
Yes.
and then to match them in a simple way. Or alternatively, you could replace dot product or whatever it is with some other kind of measure for detecting whether your motif occurs at a particular point.
Yes, so pretty much exactly what we do. When you
Yeah.
come down to the brass tacks of it, the mathematics may not be exactly what you say, but it's that is essentially what is done. Except that we have to keep in mind that all of these transformed versions are constructions from a fundamental structure,
Yes.
which is what we're trying to discover. Now,
Well,
here-
so the question is, what if there are too many transformed versions?
that's when the computation blows up, and it's not really, so yes, you're right.
So could instead of modifying the motifs, could you modify the similarity function that detects a motif so that it could use not only the motif? Sorry, I'm not using your terminology, but also look at the data at the same time. So it could, in effect, construct which transform you needed on the fly.
Well, that's implementationally. That's exactly what we do. It's just a question. It's just
So you can
that-
throw an edit distance, for example, if we were doing this on strings.
Oh yes, and we can also throw in priors over the transformation. Some are more likely than others. We can make those parts. The problem is, regardless of how we implement it, you end up computing a map for every possible, a two-dimensional map, for every possible transform, for every possible basis, weighted with or without probabilities. That's where it becomes expensive. Beyond that,
That's what's not clear to me in all domains. So let's take this offline. I mean, the question is if it's a domain like string matching rather than image matching, if you can use dynamic programming to
You
get
should be able to.
distribution
We have not done it.
over an exponential number of possible transform versions.
So our next extension here is in order to make the whole solution for this thing sparse by not considering everything, but essentially what you're proposing. Except the current implementation doesn't do that. It's not. So what you're saying, what you're speaking.
I guess actually here the obvious thing to use would be GTW. Right?
No, but just
Jason, I like the offline idea. Any other questions? No one? Right, let's thank our speakers.